Okay. We're going to start talking about classification trees. That's another classification method. There will be no time to go over neural networks, like there's never enough time to do that. But these classification trees have proven to be very powerful tools, especially with some of the characteristics that one of the algorithms that we're going to be talking about, which is called C5.0, has. So, decision trees or classification trees are essentially a way to structure the process to classify an observation, a new observation, based on the characteristics of the predictor variables. And the way they work is it's just like a tree. That's why they are called the classification tree. So there's some simple examples here. I have salary. I don't know if you see the screen. Yeah, yes. Salary, for example, this particular case, if salary is at least 50,000, then it goes to the left branch. It says, well, do you commute more than 1 hour? If yes, you decline the offers. Possibly this is an example that has to do with whether you accept or do not accept a job offer. Okay? So, if that happens, if you go this route, you decline the offer. Now, if you commute if the commute will be more than 1 hour, if it will not be more than 1 hour, then you go and you check if they offer free coffee. If they offer free coffee, then you accept the offer. And if you don't, then they don't offer free coffee, you don't accept the offer, you decline the offer. So as you can see, this can be structured as a sequence of if then else questions. If salary is less than or equal, is greater than or equal to 50,000, then if I commute, if the commute will be more than 1 hour, no, then do they offer free coffee? And if they do, then I'll accept the offer and so on. So that's the idea of the decision tree. And these nodes here are called the terminal nodes. Okay, so terminal nodes end up with the decision whether you accept the offer or you don't accept the offer. Okay. The models that are based on trees or rules consist of nested if-then-else statements, as we saw in the example, the previous example. So then we can say if predictor A is greater than a value, then if predictor B is equal to something, then the outcome is a success, else the outcome is a failure. And if the predictor A is less than 1.7, then the outcome is a failure. So any decision tree can be expressed now as if then else sequence of statements. Okay? Now, in this example, essentially, this is putting graphically this example. We have two predictors, predictor A, predictor B. And we're splitting the space. This will be the sample space, right? This will be the predictor space. In this case, we only have two predictors, so it's a two-dimensional space that we have here. And it's splitting the predictor space in rectangular regions. That's what decision trees do. Okay. Example here it's saying if predictor A is greater than or equal to 1.7, so we're on the right side of this thing. We split here the value for predictor A. Then, if predictor B is greater than or equal to 202.1, which would be this one here. That'll be this boundary here, 202.1. And if that's greater than this thing, I go the first route, it's a success. otherwise it's going to be a failure. Okay? So this is a very simple tree, a very simple classification or decision tree, and it has a representation like that. We can represent the least in this case that we only have two predictors. The advantages they have, the advantages that classification trees have, one is interpretability. Okay, that's one of the advantages that they have. The second one is that they can work with any type of predictors. So they can work with numerical predictors, with continuous predictors, categorical predictors, it doesn't matter. There is little or no pre-processing required because things like outliers and missing values are handled very nicely by these decision trees. Some people like them because they resemble the way people think. That's the way we make the decisions. And some of the methods that have been used, for example, in medicine, are translated into rules. So that when a patient arrives to the emergency room, where they say that there's a sequence of questions that the attending physician is going to ask. Okay? Or the nurse, or even the nurse, because they have their decision through rules written down, and they know them. Yeah, so they start questioning, what do you have a pain? Where do you have the pain? If you have a pain place, then they ask something else. You have fever. When did the fever start? So that's the way that people reason to make a decision. So that's why people like this decision trees. Okay. Now, they also have weaknesses. One of the weaknesses that they have is instability. Decision trees are very sensitive to the data set that we use for training the model. Okay, so if we select a slightly different set for training, we may get a completely different tree. That's why, particularly with decision trees, it is very important to use resampling methods like cross-validation. It's very, very, very important. The other disadvantage they have is that they have suboptimal classification performance. There are better methods to use for classification. It's very seldom that they can be optimal because they require to be optimal. They require that the target variable, the objective variable, be such that the sample space is being split in rectangles, and these will be hyper rectangles in higher dimensions. That will be an adequate representation of the spec. That's what they require. So that's one of the limitations of the weaknesses that these algorithms have. Now, these algorithms are part of what are called the recursive partitioning algorithms. Okay, there's more of those algorithms. The only ones we're going to see here are the decision trees, but they are part of recursive partitioning algorithms. And one of the advantages of the recursive partitioning is that the implementation is very easy. Okay? Now, this is in general how the algorithm works. We set the optimization criteria. What do I want to do? Maximize classification, correct classification rate, or whatever. And then, based on that criteria, the algorithm proceeds and starts checking the different variables that I have, and then selects the best way to partition the data. Okay? So the observations are split in the groups defined by this partition, and then we'll repeat the first step. So the way it works is, let's say in this case I have
in the previous slide, we have two variables, right? Predictor A and predictor B. Yeah, A and B. So let's assume that we take a very simple criteria and say that I'm going to choose, I start with A, for example, and then I choose all possible values of A that I have in my training sample, and check for those values what's the best split of the data, in the sense that I have most of the observations belonging to a success and the smallest in a failure. Once I determine that, then I say, for example, the partition, let's suppose that I start with A, and then A can take the values from whatever, here I have A. So for the different values that I have in the sample, in my training data, I check if I use this value for A to partition the sample space in two parts. And in one part, I get 80% success and 20% failure. That's with this value. And then with this value, let's say I get 60% success and 40% failure, and so on. So it would pick the one that gives me the most clear definition of a result, of the most clear chances of getting the right result. So it would pick this one, okay, because it gives me a mixture of 80-20, which is better than 50-50. 50-50 is flipping a coin, and 80-20 is not flipping a coin. And now it goes in all the values for predictor B, it does exactly the same thing for predictor B. So I have predictor B, which can take several values, and it checks for each one of those values how the data is partitioned. And let's say that I pick this value here, and it turns out that the partition here would be 50%, 50%. And this one here, this one would be 90%, and then 10%. 90% success and 10% failure. So the first split would occur, in this particular case, it would occur for predictor B at this value, okay? So this value was 2.7, okay? That would be it would choose this value because I got the most clear signal of which is the right response, success or failure. Okay? So that's the first node. That would be the first split. So I take my first split with predictor B, and my tree would start looking like this. I would say if B is, this is 0.7, if B is greater than 2.7, I'm going to go that way, and if it's less than or equal to 2.7, I'm going to go that way. For the next split, that's my first split. For my next split, what it's going to do, it's going to check again A. Now I have two subsample spaces, right? Once I partition my data, I have two subsample spaces. We go back to this chart here. Once I partition the data, I have, for example, in this case, this would be predictor A. That was the first one it chose, right? The predictor A is greater than or equal to 1.7. Once I know that that's my first split, then I have two sets of data. I have the data to the right of 1.7 and to the left. And then what the algorithm does, it takes this data set and this data set, separate data sets, and does the same procedure. So it takes this data set and says, okay, now I'm working with this subsample. Okay, it's a subset of my sample space, and I'm going to check again for A and B. So I check all possible values of A and all possible values of B, and it turns out that in this case, the best split I got it with B equal to 200 something, right? 202.1. That was my first split. Then after that, I have a large proportion of successes in these blocks, and I know how to classify the new observation, data point. So that's a procedure, that's a general procedure of for tree. I don't know if it's clear what we're doing. We're splitting the space in two every time. And then we're working with the subspaces that we obtain, check all the predictors again. So all the predictors are checked again. So that's we repeat step one for each of the partitions. Then the next time we'll have 4 partitions or 3 maybe, depending on what how we split the data. And then we check we do the procedure again. Validate all the variables and all the possible values of those variables. Okay. That continues, the process continues until I have a stopping criteria. The stopping criteria could be until I get a tree of depth, let's say 10, okay? Or until I get a minimum of 10 samples in each terminal node. That would be another termination criteria. Another stopping criteria could be just finish until the difference in proportions of success and failures in a terminal node is greater than 30%, for example. So I can have several stopping criteria. Now, the way we do splits is not as simple as just computing percentage of observations live in each side of a node. Okay. The objective that we're pursuing with this thing is to get sets. Once we do a partition, we want to get subsets of that sample space that are as homogeneous as possible. Okay. So if I have if I define a split where I have 50% success, 50% failure, I don't have clarity there. So I would want to do split in a place where I have more than a larger difference in percentages, for example. So this is essentially what I said earlier. The division of sampling space is performed for all different values in the training set, all different values for the predictors. And we evaluate all possible predictors. So for all possible predictors, we evaluate all the possible values to do a split, and those values come from the sample from the training data set. So that's where the values come from. Okay? And then we select the predictor and the value, which gives us the highest purity. What we call purity, for example, if I have a split, let's say predictor A, and that difference was like 2.7 or something like that. If to the left I have 80% success, and to the right I have 20% success. And for the value, the same predictor A, I get another value, I pick another value, let's say 1.5. And then here to the left, I get only 65%, no, 60% success. And to the right, I get only so 60% for the success here and 40% failure. And this would be at 40% of the sample will be here, right? 40% of the data points will be here, 60-40, that proportion. So we say that this node, this node is more pure than this node here. Okay, so the larger the difference, the easiest it is to classify an observation based on the percentages, then that's a measure of purity. Okay, so we select the split and the data and the observation that gives us the largest purity. That's how we select the splits. Now we will see that there are 2 ways essentially that we're going to be measuring purity. There will be 2 ways to measure purity. we'll define it a little bit later. Now, the simplest way would be to use purity the way that we're using it, okay? As getting a large percentage of successes and not getting, as far as I can get from 50-50%, that's the more pure I get, the more purity I have. And that would be that one criteria. But turns out that criteria is not the best criteria to use to define the splits in a decision tree. There is other two criteria. One is called an entropy. That's one of the decision criteria that the purity criteria we're going to be using. And the other one is going to be the classification. One is information measure. We have an information measure and the okay. Now that will be one of the measures that we'll be using is Gini's index. Have you heard of Gini's index? No? In demography, they use it to, for example, when you have people in a certain region have very similar socioeconomic conditions, then that's a measure of how equal things are for those people. So Gini's index is something that the sociologists and the economists use to measure unequal economic opportunities. That's essentially for what it is measured, what it's done. This is very similar. It's the same idea. The more inequality I have, the smaller the Gini index is going to be, and that's a more pure. That's the more pure node. Okay. So that's one of the measures. Actually, the different algorithms to do to train a classification tree are based, the differences in which criteria we use for purity, and again, we only use Gini's index and entropy that comes from the theory of information. Oh, Gini's index is also called deviance. Okay? So this is related, remember we saw logistic regression that we talked about the deviance? This is related to that deviance in a sense of when you put distributions behind these things and you talk about maximum likelihood, this deviance is related to that. But that's the Gini's index, and that's one of the measures, and the other measure is a cross entropy, which is cross entropy. We'll see the definitions now, but cross entropy comes from information theory. From communications, from telecommunications. That's where the term cross entropy comes from. Okay. Now, here, a predictor and the value of that predictor are chosen to build the first node based on purity. The variable, the selected value, are those who achieve the best separation among the groups because we want homogeneity within each of the subgroups, okay? But the differences between the two groups. So that's the one that achieves the best separation. Now, if the target variable is binary, then there is only one separation. If the target variable is continuous, for example, these trees are also used for regression, okay? Regression, they are called regression trees. And if the continuous variable, if the predictor, if the target is a continuous predictor, a continuous variable, then we use regression. And then if we have n data points, we will have n minus 1 possible separation points to do the split. Now, if the continuous variable is regression, these regression trees are not the best tool to use to do prediction. There are much better methods to do prediction in the regression case. Yeah? But then after the first the best separation is found, we divide observations in two groups. The group of observations for which x is less than the average of the 2 points that are closest, and the observation for which x is greater than or equal to that b. That's in the case of regression. Okay? And then in the case of regression also, as well as in the case of classification, the variable selection process is repeated for each of the subgroups that we're forming. That's repeated for each subgroup that we're forming. The most basic trees are the CART algorithm. CART is for classification and regression trees. Okay, we'll be focusing more on the classification part, because for regression there's other methods and that are better to deal with continuous response variables. Now, for a two-class problem, Gini's index is given by, if we have a two-class problems, then we'll have two probabilities. P1 is probability of success, and then P2 would be 1 minus P1 would be the probability of failure. And Gini's index is essentially 2 times P1 times P2. That's what it is. 2 times P1 times P2. And P1 and P2 are probabilities of belonging to class 1 and class 2 respectively. So that's Gini's index. Okay? And that's one of the criteria. That's the criteria that is used in the CART model. Now, what we want to do is minimize Gini's index. The smallest Gini's index is, the more pure is that node. Okay, the more purity we have. So the objective is to minimize Gini's index. And when we minimize the Gini's index, when either P1, when either the probability of success or the probability of failure tend to 0, right? That's when Gini's index will tend to 0. What will be the maximum value to, when will the Gini's index be a maximum? Remember when you studied the binomial distribution? What was the most pessimistic estimate of variance? If you didn't know what was the value of P, the probability of success. Remember what was the conservative estimate of variance? If you didn't have any idea, it will be with P equal to 0.5, right? P equal to 0.5, that's what we have the largest uncertainty. Okay, it's like P equal to 0.5 is like pretty McCormick. So we have that would be the maximum value for Gini's index. And so we want, in that sense, this is related to what I was saying in terms of splitting the data, because it's looking essentially what proportion of the data, what proportion of successes we have on either side of different values for the different variables in the predictor space. Now, the process to find the optimal split is to order the observations so that we minimize the Gini's index. So essentially, we compute the Gini's index. Let's suppose I have a sample where I have my values for A and my values for B, and A goes like 1 minus 1, and 0.5, 0.7, 1.1, and so on, and B takes values 105, 150, and so on. Okay? I have different values for the same. For each value of A and for each value of B, I check what's Gini's index if I take a particular value of A with one, for example, what would be Gini's index if I take A equals to -1 as a splitting point? Then I compute what will be genius index if I take A equals 2.5 as a splitting point, and so on. So I keep computing the genius index for each of these combinations, these possible values. And then I do the same for B. What if B is equal to 1.05? What would be genius index when I split the data? What would be the genius index if I take 150 for value B? And I select the value, the variable that gives you the lowest genius index. That will be for defining the first split. That's a contingency matrix, okay, where we have the two classes, and then we have here the value. We're going to select the value so that if the variable is greater than that value, then I have N11 observations classified as N1 as class 1, and N12 classified as class 2. If I have less than my variable takes a value less than the split, then I will have this number of observations assigned to class 1 and this number of observations assigned to class 2. And my totals, my raw totals, this should be a lowercase n. Okay? This will be my raw totals, and these are my column totals. Then I compute genius index before the split. So I take, before I do a split, what's the value of genius index? Okay. So before the split, the value of genius index will be 2 times this is the n plus 1. This is the usual notation for contingency tables. That will be the total for column 1, because that's the total for class 1, and plus 2 will be the total for class 2. That will be, because it's 2 times that, because I'm estimating these proportions P1 and P2, which are the probabilities of class 1 and class 2. I'm estimating P1 by n plus 1, which is the total of observations that I have in class 1 for this particular split, and divided by n, which is the total number of observations, and n plus 2 divided by n, which is the estimate of P2, the probability of class 2. Those are the sample estimates of those probabilities. Okay? So before I do the split, I compute the same. And I compute the same for all possible splits. So I take all possible values where I can do a split, and I compute the genius index before the split. Okay? Then you can imagine what's going to happen later. I'm going to do after the split and check which of the splits gives me a smallest, largest reduction in the genius index. So this index then is calculated after the split then. Okay. So if I were to do the split that I had in the previous slide, then I compute here what's genius index after the split within each of the new node values. So after the split, I would have, this will be genius index after the split for the greater than split. Okay, this is for the greater than split. And this will be for the less than or equal to split. Because after I did the split, then if I'm on the greater than or equal, in the greater than, then what do I have? I have in class 1, I have N11, right? And I only have, my total would be, my sample size total would be N1 plus in that case. So that's how to compute the genius index after the split. Okay, because I have N11 which is now my estimate of P1 for the greater than split, N11 divided by N1 plus, because that's what I have, that's the number of observations that are left in split 1. And then I have N12 divided by N1 plus is my estimate of P2 after the split. Likewise here, this is the estimate of P1 after the split, after the less than or equal split, and this is my estimate of P2, the probability of class 2, after the second, after the split, for the less than or equal split. Okay, so this will be my P2 estimate. P2. This is my. This will be P2 estimate, and this will be my P1 estimate for this split. And here, this will be my P1 estimate and my P2 estimate for this split, for the greater than split. Now, then we combine these values using the proportion of samples in each part of the split as weights, because I have to weight when I combine them, I need to weight them because of I have different number of observations in each of the splits, and numbers change. So I need, after to combine these values, then I weight them with n plus 1 divided by n and n plus 2 divided by n, because they represent the respective weights, which are the proportions that are left in the after the split. And finally, Gini's index to evaluate if that is the right split would be, I will measure Gini's index after the split, and that will be 2 times my estimate of probability of success for the greater than split so this is my estimate of success for the greater than split, and this will be my probability of success for the greater than or equal split, and likewise for the less than split. Okay, but and that will be my Gini index after the split, and then that will be what I use once I have Gini's index before the split and after the split. The point and variable that is chosen to do the split is the one that achieves the largest reduction in the differences between Gini's index before and Gini's index after. Okay, that's how we would select the right split. This is an example with some numerical data there. We have, for the greater than split, we have the number of observations in class 1 is 91, and 30 here, and so on. So a total of 208 observations in this case. Okay? And then I have the Gini's index for the split, and then the weights, these are the weights. And the overall Gini's index is 0.365 for this particular split. Okay. Now this is done for all possible splits. So this is done for all possible values of the different variables. So if I have 80 predictors, then and each predictor has, let's say I have 2 million observations for each of those, for my training data set. Then I have 2 million possible values for each of the predictors, and for each of those I will be evaluating before the split and after the split to select the one. Okay? Now the algorithm is optional. It says it doesn't go exactly absolutely for every possible value. but there are some shortcuts those are to the algorithm that we will not get into here, because we're not going to get into the exactly how the algorithm is implemented, but implementation has some nice computational tricks to make it more efficient. Okay. So for the observations in the split, b greater than 0.97, this would be 0.373, and 0.354 for the observation with p less than or equal to 0.97. This is an example for this particular data set. Okay, when we're taking the split with p, the variable b. And if we want to know if that's a good split, we combine the values. That's the procedure. Okay? Let me go here. Okay. So here, the weight for b greater than 0.197 will be 0.582, which is this value here. And for b less than or equal to 0.197, it will be 0.480. That's the weight. So the Gini index for this field would be 0.365, which is what I have here, that example. Now, once we determine which is the best place to split, after evaluating all possible bifurcation points, so I need to evaluate every possible point where I can split the data. And after evaluating all of those, we select the one that gives us the largest gain in Gini index, that is the largest reduction in Gini index, until when do we stop? We stop until the stopping criteria is met. Stopping criteria could be a maximum depth of the tree, or could be a minimum number of observations in a terminal node, or some other criteria. We'll see that some of the algorithms have a complexity criteria that determine how far deep, how far down the tree we should go, and compensate, because the farther down we go, the more complex is the tree. Okay? And the more, if we have overfitting, when we do, if we do a tree with maximum length, that is, when each terminal node ends up with one observation only, then that will be an overfitting. That will be overfitting the training data, and that's not a desirable thing to do. And that's what it says here. Trees of maximum depth overfit the data. Okay. So most of the tree algorithms have a pruning procedure. Okay. So some work like that. Some algorithms and work like CART algorithm works like that. CART builds the tree of the longest depth and then starts pruning back according to some criteria. And the criteria could be based on a cost complexity parameter, that would be a hyperparameter that we will have to select by cross validation, by resampling method, or could be a criteria like I want a minimum of X number of observations and start pruning back until I get a minimum of 5 observations in each terminal node. So the most common one is this one, to use a tuning parameter, which is hyperparameter, which penalizes the purity criteria by a factor of total number of terminal nodes. So the larger the number of terminal nodes, and because in one extreme, if you look at that case where you have 2 million records, 2 million transactions, you could have 2 million terminal nodes that will overfit the data. So there's a parameter that most of the tree algorithms that we'll see have, which is a cost complexity parameter that will penalize the purity by how much depth the tree has. Okay? Now, classification trees can handle missing values. There's only the observations that do not have missing values are considered for splits. If we have missing values, there's a way we can consider that for a split. So missing observations, missing values don't really impact in the tree construction. We have mentioned the same. If a predictor is continuous, bifurcation it's clear because I have a continuum of values for a given predictor. So I choose the different values and select and measure a Gini index before and after, and I pick the one that gives me the largest decrease in index, in Gini index. Okay? But when they're categorical, there's two routes we can follow when the predictors are categorical. We can handle them as a bunch of dummy variables, okay? Let me see, which is the approach that's used in logistic regression. And that is called independent categories, okay? So if we assume that the categories are independent, then the categorical predictors are decomposed into dummy variables. And the other case is when we handle the categorical variables as grouped categories, okay? So in this particular case, each categorical variable enters just the way it is, enters just as it is, if it has 5 different categories or whatever. And then the algorithm will start grouping categories depending on how the splits are working when we're building the tree. This is an example from a given data set. This is comparing some methods that we already that we will be seeing here, not all of them. We've been talking about the CART algorithm, which is classification regression trees. BART is very similar to the classification regression trees. We'll talk about C5.0 here and random forest. Those are the ones we're gonna be working with. And this is the difference in performance in the area under the curve, sensitivity and specificity for the grouped categories, which is like a little O there, and independent categories. So as you can see, there's not much of a difference. There's some larger differences in some cases, but the cases that are of more interest to us because of the practical applications are C5.0, where it doesn't make much a difference to use group data, to use group categories, or independent. And the other one that we'll be using is random forest, where also there is no big difference, not only the area of the curve, but also on sensitivity and specificity. So in general, we will not worry about this thing. We'll let the algorithm deal with the categories, unless we have a good reason to consider them as independent categories, and then we will need to code them in a binary form with dummy variables, using dummy variables. But that really depends on the issue. Now let's look at this algorithm. This is the CART algorithm with the iris data. You remember the iris data, we've seen it before. We have 3 different types of iris flowers, and we are measuring several characteristics, sepal width, petal width, and so on. Okay. We'll look at the case where we're looking at 2 of the predictors, which is sepal width and petal width. Okay? And we'll go over, I'll give you the breakdown. It's 10:55. We'll come back at 11, let's see, 10 minutes on 11:10. Okay? 11:10, and we'll go over this example. Okay? Any questions for those of you who are at home? No questions?
No, teacher.
Okay. Well, we'll see you in a few. Let me stop sharing and do this. Now let's look at how it works. How this algorithm works with the IRIS data. And as you can see, I'm considering only two variables here: the petal width and sepal width. And if you recall, those were two variables that were really the most important to classify between the three types of iris flowers. Okay. Now, what the algorithm did is start checking all the possible values that you have for the two variables that I'm considering here, petal width and sepal width. Turns out that the first one that it chose for doing this first split was petal width. Okay, that's petal width. That's the first one it chose to do the first split. How did it choose it? Again, it evaluated all possible values of petal width in the training data set, then computed genus index before and after, did the same thing for sepal width, and turned out that the last year's reduction in genus index was obtained by the petal width equal to 0.8. Okay, so that's the first split. So it says, well, my first split is petal width. Now I have two subsamples, okay? I have two subsets of my training data. The one that's here on the right, where the petal width is greater than or equal to 0.8, and the one on the left, where petal width is less than 0.8. Now, if you look at this separation, one of the things is going to be clear is that on this side, on the left side of 0.8 petal width, on the left side, all the observations belong to one class. All of these are setosa. In this side, all of these are setosa. So on the left, there's nothing else to do. The tree will end there because I don't have any single case of any of the other iris flowers. So 100% of the data on the left of the petal width of 0.8 is setosa, corresponds to setosa. So now it goes to the right, okay? It goes to the right side. I'll start focusing on this side, and that's my new subset of data for my training space. And now it will evaluate petal width again. Remember, the first variable is petal width, right? Now it will check again all possible values of petal width and all possible values of sepal width, and see which value gives us the largest separation in the groups, in the two classes that we have left, because we only have all setosas were left in the left side. So I have now a mixture of two classes here, versicolor and virginica. Now, it checks again all values of petal width. So for each one of these values, for each value of petal width, computed the genus index for each value, and it also did that for each value of sepal length. For each value I have, it computed the genus index. And then it determined which variable value combination gave the largest reduction in genus index. And turns out that it selected again petal width. So it selected again petal width, and it selected the value of 1.75, okay? So the next split is that one. It's selecting a petal width to the left of 1.75 and to the right of 1.75. And now I have, if you look now on the right side of 1.75, all of the flowers there are Virginica. So I would not expect any further separation there. However, on the left side, I have some cases of Virginica and some cases of versicolor, although versicolor is the one that dominates there. So it checks again all values of petal width and all values of sepal width. It checks again all the values. And then it's going to look at the one that gives us the largest reduction in Gini's index. So after it checked all possible values, it turned out that, again, petal width is the variable of value which separates the samples better, and that'll be the third split there. Okay. So it says now, if everything to the left of, if you look at this, this separation it did, everything to the left of 1.35, and of course greater than, because we're already in the greater than 0.08, all of these are versicolor. And the only subsample where I have a mixture of both is this one on this section in the middle. And now it selects for all the values of petal width and all the values of sepal length, which value separates better the samples. And it selected now a sepal width of 2.05. Now it selected this one. Sepal width of 2.05. Because if you look at that sepal width of 2.05, turns out if you go in the above the 2.05, that is to the right side of this strip there, it classifies the data as versicolor because that's the largest proportion. See, I have 2, 4, 5, 6, 7, 8, 9, 10, 11, 12 out of 14 data points correspond to versicolor, so it assigns those values to versicolor. And here, you look at this split on the below this line, I have majority is the one with green, the Virginica. So these will be classified as Virginica. So in a sense, the algorithm is misclassifying. What is it misclassifying? It's misclassifying this one and this one, because those are not versicolor, and it's misclassifying this one. So I have 3 observations that we classified erroneously. That's how the algorithm works. It always partitions the space, the predictor space, in rectangles.
Teacher, and what happens with the ones that are the outliers that we have there, or are they outliers, or how do we consider those?
Could you repeat the question?
What happens with the values that are circled with blue?
Oh, these will be misclassified, okay? The algorithm says that everything above this line and between these two vertical lines is versicolor. So it is misclassifying those because these are Virginica and we classify them as versicolor. And likewise here, everything below this line is being classified as Virginica, but this one is a versicolor, so it's misclassifying that.
Okay. So, and that would show in the GG index or the index we were seeing?
Now, the GDC index is computed to define these points, okay, these split points. So
Okay.
GDC is computed before and after each split to determine these partition points, these splits. Now, here the classification goes with the largest percentage. So if here it's classifying all the observations that fall here will be classified as versicolor. Okay. All of them, all the observations that fall on this side of the tree will be versicolor, will be classified as versicolor. Okay. So it's based classifying two observations that correspond to Virginia. Is that clear?
Yeah, it's clear. And how do we know when how many misclassifiers we can have, or how much error can we accept?
Well, of course, you want to have, in this case, we have balanced samples, right? We have 50 observations from Versicolor, 50 Virginica, and 50 Setosa. So there's balance in my training data. So the criteria could be to maximize the correct classification rate or minimize the incorrect classification rate, the misclassification rate. And this will be very reasonable because it's only 150 samples in total, and I'm only misclassifying 3 out of 150. So the correct classification rate is very good. Okay? Now, of course, the classifier, what you want, if the criteria is correct classification rate, you want a classifier that gives you the maximum percentage of correct classification. If the criteria was area under the curve, then you would want a classifier that gives you a maximum area under the curve.
Maximum error under the curve. Okay.
Okay? And that's why we always compare algorithms. Okay? We would never just go ahead and use this algorithm. We would need to compare this algorithm with a support vector machine, with a logistic regression, and so on.
Okay.
Okay? To select it. This is using the function R bar from the target algorithm, and this is another way of displaying the tree. Okay. Here you can see the way that the tree is displayed. Looks a little bit nicer than the other tree that we just saw. And it tells me, for example, if you look at the first node, Setosa, it has 33, 33, 33, because I have 33% of Virginica, 33% of Versicolor, 33% of Setosa. Okay? Now, once I do the first split, on the right side of the tree, I have a versicolor is the class that dominates. Okay, the versicolor is the class that dominates there, and I have 0%. That's why the first zero here is 0% of Setosa, 50% of versicolor, and 50% of Virginia. So, and the number of the observations that fell on this side of the tree were 67% of the observations. On the other side, on the left side of the tree, all of them were Setosa. So I have 100% of the observations in this side of the tree are Setosa, and 0% Virginica, 0% versicolor. Okay. Now, on the right side of the tree now, remember there was a second
split, and this one is split here with the petal width less than 1.8 and greater than or equal than 1.8. And if it's greater than or equal to 1.8, it's classifying the flower as Virginica, because that's the largest percentage, right? I have 98% of those that fall on this side are Virginica, so they will classify all of them as Virginica. And on the ones that are less than 1.8 for the petal width, they will be classified as versicolor because that's the largest percentage. At 91% versicolor. Okay? And that's the split here. That's the first split. Then it'll be the second split, this one here, with versicolor here, petal width less than 1.8 and greater than 1.8. And this is another form to look at the tree. This is another form to look at the tree. It's giving me graphically what you see here. For example, move this here. See there, it gives me all the, you cannot see it here on the screen. Minimize this. Yeah. So it's a different way to present the results. And here I have the percentages on this one here. And here I have the percentages but in terms of bars, right? So I have 100% Setosa on this side, on this terminal node. On this terminal node, I have 90-some% of Setosa of versicolor, and here I have the largest percentages of Virginia. So those are the terminal nodes. So as you can see, the tree is similar to the one before, but it is a different algorithm, and it ended with just 3 terminal nodes. 3 terminal nodes. The previous tree we saw had 1, 2, 3, 4 terminal nodes. Okay, 4 terminal nodes. And then this is a tree of depth 1, 2, 3, 4. This has depth 4, and the second tree with the part algorithm, part is its depth is 3. It's 1, 2, 3. Some people counted from here with depth 2, but it was not. Now we're going to do the same with the hard data, hard disease data. And we've dealt with this data set before. We have very few variables. Now, one thing that's important to know, these trees have a nice visual representation if we have a small number of variables, and because we can keep it to a reasonable size. If we have 8 variables, then the visual representation of the tree will be very messy. You couldn't really read it. So the visual representation works fine when we have a reasonable number of variables. And the tree is not too, it has not very large depth. So this is with the heart disease data. So heart disease data, remember I have age, weight, gender, VO2 max, and the diagnosis, if it was heart disease or not. And remember that VO2 max is heart rate during exercise, okay? Gender, weight, age, and so on. So we did the classification using other methods for this algorithm, for this data set. For the tree algorithm, it selected age as the first node. The first split is given by age. If age is less than 34.5, it automatically classifies every observation as no heart disease. Remember, 0 was no heart disease, 1 was equal to heart disease. Then it went over all the variables and it selected weight. And if weight was greater than 93, then it goes to the right. And then if weight is greater than 93, greater than or equal to 93, then age is the next variable that it selects, and it chooses, it assigns it as heart disease. Now look at this thing. In both branches of this last node on the right side of the tree, both are classified as heart disease. Now, why does the algorithm separate? Why the algorithm separates this and this as one, only has one? That's it. The only difference is the percentage. Okay? And in one of them, the percentage of heart disease in that side of the branch was much higher than in the other side. Okay? That's why it's split. You see sometimes it splits. But in any case, the algorithm, when it comes, it checks if age is greater than or equal to 93, and the age is less than 41.5, is less than 93. But in less than 41.5 is heart disease. On this side, it has more nodes. Okay? So the trees can have much more nodes on one side on one of the branches than in other branches. That's a natural thing because it depends on the responses. Here, on this side, checks the weight, it's less than 93. Well, now it checks, and if it's less than 75, and its age is less than 45, and gender is less than 0.5, which is zero, right? Gender it's a female, then there's no heart disease. It also classified as heart disease. However, if weight is greater than or equal than 75.45, and gender is greater than or equal to 0.5, and weight is greater than or equal to 87, it's heart disease. If weight is greater than this, but gender is female, it's not heart disease. Okay? That's it. So that's it. That's how these trees are built. It's always making choices between which variable to do the partition by, select the split, and then work with each side of the split, each of the two sides of the split separately, do the procedure again. Are we doing okay so far?
What was that?
Are we doing okay so far?
Yeah. Okay.
Okay. Okay. This is another representation of the same tree with different algorithm, right? This is the card model. This one has let's see, 2, 3, 4, 5, 6, 7, 8, and 9 terminal nodes. 9 terminal nodes in this algorithm. So each algorithm will give us a different tree. The next algorithm, raise this thing. The next one, which is the card model, it gives us only 4 terminal nodes. Okay. But again, here we have the classification. We have The first variable is age. Now the number changed, right? In the previous algorithm, it was 47, something like that. Now it's 41. If age is less than 41, it will classify as non-heart attack. Because 52% of the data, what this notation says is that the 52% of data fell on the left side of the first split. And of those 52% of the data, 16% have a heart attack. So the majority have no heart attack, so no heart disease, so it will classify them as no heart disease. On the right side, if age is greater than or equal to 41, so here, on this side. Now, the next variable is weight. If weight is greater than 93, it will classify it as heart attack. Because I have 100% of the observations in the training data set that fell on this node had heart disease. Okay? If, on the other hand, weight is less than 93, then it checks for weight. If weight is greater than or equal to 77, then it classifies them as heart attack, because 54% of the 18% that fell on this node had heart disease. But if they fell on this side, they were classified as not having a heart disease. And the tree on the right is the same, just a different presentation with bars. Okay, denoting the percentage of heart disease present in that node at the end of the tree. Okay, that is with the heart data set. Okay. Now, I was saying earlier that the three algorithms are usually not as good as some other algorithms like neural networks and supercomputer machines classify. However, there are some modifications that have been done to three algorithms that make them work very well. We'll review first the C4.5 algorithm, which is the predecessor of C5.0. C5.0 is an algorithm that incorporates many good characteristics that make it a very powerful algorithm for classification. Okay. Now, these were developed by Quinlan. C4.5 algorithm was developed by Quinlan. And it's working. Let me change my USB to more. It was working this time. Now, in this C4.5 algorithm, the criteria is not based on Gini's index, it's based on the theory of information, on entropy and cross entropy. And this comes from telecommunications. Suppose that we want to communicate a certain flow of information. You have to communicate from one place to another, certain flow of information. For example, a probability distribution of we have classes, so we need to try to transmit the probability distribution of these classes that we have through a series of messages. If the probability function is extremely unbalanced, that is, if the probability of success is very, very high relative to the probability of failure, then I will need to transmit less information to be able to make a decision. Okay? So the more unbalanced I have, in the probabilities for the classes, the easier it's going to be to make a decision. If the class probabilities in the nodes were very similar, then I would need to provide more information so that somebody can make a decision, classify something as heart attack or not. If the rates were very similar, if the probability of heart attack was near 0.5 or 50%, and then I would need to provide a lot more information to be able to classify a patient as having a heart disease or not. If, however, the probability is much lower, for example, if I have a 1% probability of having a heart disease, then I need to provide less information to be able to classify a patient. So we need to transmit more or less information depending on that balance between the classes, the balance that may exist between the classes. The amount of information that this comes from telecommunications theory represents the number of bits needed to communicate the message. So the more bits I need, the more balanced. That means that the classes are very balanced, balanced. For simplicity, let's take the case where we have two classes only. We have two classes only, then and the probability of class 1 is P, then the definition of the information statistic is this: we compute the information statistic as minus P log base 2 of P plus 1 minus P log base 2 of 1 minus P. Why log base 2? Well, log base 2 because this comes from communication theory, which is, remember that a computer works based on zeros and ones, that's it. So it's that's why the log base 2 is used for this statistic, for this information statistic, because it has its origins in telecommunication theory. So that's the definition of the information statistic. Now, if P is defined, if P is equal to 0, then we define the log base 2 of P as 0 times P. The log base 2, 0 times log base 2 of P is going to be 0 when P is equal to 0. Okay? That's by definition. That's by definition. You cannot compute the model. Now, for the two classes that we have here in these are the similarity data that we have seen before. The proportion of observations in the first class is 52%. So the classes are balanced. They are balanced. In this case, if you compute the info statistic, information statistic is 0.997. So that means that I would require to transmit 0.997 bits of information to be able to classify an observation. But to be able to understand the message, If instead we consider the case where P is equal to 0.1, then information will be 0.46. So what happens for Gini's index, we want this information to be as small as possible. Okay, so in Gini's criteria, or the entropy criteria, we want the smallest value as possible, and that will be the criteria that the C4.5 algorithm uses. That's the one that it uses. Now, splits are determined, it's similar, in the case when we use Gini's index, it's similar, but instead of Gini's, we'll use the information. Okay? The information statistic. Using the notation that we used earlier, when we have our contingency table and total of observations, and Y1 and Y2, and so on. That's the same notation we used earlier for the contingency table. Then we compute, instead of Gini's before the split, we compute the information before the split. Okay? And information before the split is in the proportion that falls in class 1 times, which is my estimate of the probability of success, times the log base 2 of that probability, minus the proportion that belongs to class 2, times the log base 2 of that estimate of the probability of class 2. Okay? Now we can measure the improvement in the information criteria that will be induced by a split the same way we did earlier. We compute information before, information after, and remember, information we want it to be as small as possible because that's the requirement of information. Okay? So the gain after a split will be computed as info before the split minus the info after the split. And that will be the criteria to select the variable and the value for the splits. This statistic, this information statistic, is also called the statistic of neutral information. That's another name. Again, that name comes from telecommunications. Now, for the binary split of a content of a table, the information of the split will be the sum of the information values for each of the partitions. It's exactly the same mechanic that was used with Gini's. Exactly the same mechanic. So we have information for the greater than split and the information for the less than split. Remember that in our table we have a greater than split and less than or equal to split. And we have our table here, right? So we compute the information for the greater than part of the split and the information for the less than or equal part of the split. And then what we do now is the total information will be, just as in the case of Gini's index, will be the weighted average of the information greater than and information less than for the greater than split or the less than split. So the information after the split will be, it's a weighted average. So I'm weighting by the number of data points that fall in the greater than split, okay, after the split, n1 plus divided by n times the information greater than n plus n2 plus divided by n, which is the weight for the times information for the less than split. Okay, the same logic that is used to compute the gain when we are using Gini's index. Okay. Now, to correct for the bias, because if we have categorical predictors, there's some bias that sort of benefits categorical predictors. So to correct for that, we use a gain ratio instead of using just the gain. We use a gain ratio, and that's the ratio between the gain and the total information, the corresponding split. But that's just to correct for bias. And that's essentially the algorithm. As you can see, it works exactly the same as with Gini. There's some minor thing here because with information, the categories of predictors tend to have sort of a preferential treatment, let's say, a preferred. So to remove that bias, that's why we compute the information gain ratio instead of the information gain only. And that's a C4.5. C5.0 will use exactly the same logic, but it incorporates other things. One of the things it incorporates is what's called boosting. And boosting is something that has made decision trees very, very powerful. See, this concept, the boosting concept, was developed originally for classification, but now it's also used for regression. In fact, it does not only apply to tree algorithms, it also applies to other methods. We can do boosting with support vector machines, we can do boosting with neural networks, with logistic regression, and so on. That can be done. It is essentially an approach to improve predictions in decision trees. It was born there to improve predictions in decision trees. But it's applied to other cases also, not only to decision trees. Now, the process is very simple. What boosting does, it sequentially builds trees. Each tree is grown using the information from previous trees. So I draw a first tree. Essentially, in simple words, what this does is the following. I build a tree, then check that with that tree, I review which observations were misclassified. The observations that were misclassified by that of initial tree get higher weight, and I recompute the tree having more weight, giving more weight to the observations that were misclassified by the first tree. I do it a third time, a fourth time, and so on. So I can do as many boosting iterations as possible. So each tree is trained with a modified version of the original set. Each tree. Once the first tree is trained, the second is trained with the residuals of the first tree, and the process continues up to a number k of boosting iterations. Okay? K can be anything. Can be 100, can be whatever. Okay. We use a shrinkage parameter, we call it here lambda. That's to make the process either speed up or slow down. Okay. We can think of this shrinkage parameter as a learning rate. How fast do we want the tree to learn? That's essentially the objective of this shrinkage parameter. This is essentially the algorithm for boosting, for k-boosting iterations. We're working here with two classes, just to simplify also notation. We present class 1 as +1 and class 2 as -1. Then each observation receives initially the same weight. Each observation weighs 1/n, n total number of observations. Then we fit for k equals to 1 up to capital K, which is the total number of boosting iterations. We fit a weak classifier using weighted samples and calculate the kth observation error. That's denoted by E, I can read what that is, RRK, error, ERR for error, for little k, for the kth iteration, okay?
And then we calculate the kth state value as the log of 1 minus the error divided by the error at the kth iteration. Okay? We update the observations weights, giving higher weights to those that were misclassified. So we reweight all the observations instead of having equal weights as it happened the first time. The second, third, and fourth time, the weights will be larger for observations that were misclassified. We do that capital K times. And then once we did the K boosting iterations, we calculate the prediction for each of the observations that we want to predict. And all we do is if we sum, remember we're classifying as class +1 or -1. So we sum the different predictions for the K, capital K boosting iterations, we add them up, and if it's positive, we assign it as class +1. If they are negative, the sum is negative, we assign it as class -1. Okay? That's essentially what it does. So it computes several trees, and then with each tree, you classify observations, and at the end, you add the K classifications that you did for all the observations you're classifying, and if the sum is positive, you assign it to class +1, and if the sum is negative, you assign it to class -1. And finally, the C5.0, this is an algorithm that has worked very well. In the project we did with a bank here in Mexico to prevent money laundering, they wanted an algorithm that could be translated into rules, into if then else, so that they could justify when they stopped the transaction or investigated a transaction as possible, as being a possible money laundering transaction. The C5.0 worked very well, as well as the support vector machines and other languages, and more black box. The advantage over C4.5 is that it includes boosting. So C5.0 has in its algorithm the capability to do boosting. And it also incorporates a cost matrix. So I can have a cost matrix to, if I may have different costs if I misclassify. For example, in the case of money laundering, I can, one is, it's an unusual transaction. We call it here unusual. I'll call it, just for shortness, I'll call it money laundering. Right? 1 is money laundering, and 0 is no money. Okay? Now, my actual, this is my actual 0 or 1, and my predicted 0 or 1. This is the predicted. If I have a transaction that is not money laundering and I classify it as money laundering, I have a cost here of that mistake. If I have a transaction that is money laundering and I classify it as not money laundering, I have no cost here. Now it turns out that the cost of classifying a transaction which is actually a transaction that's unusual because it's money, it's very likely that it's money laundering, then the penalization, the penalty for the bank can be very, very large. So my cost here is much greater than if I make this mistake. Here, if I make this mistake, all I'm doing is I'm incurring costs to investigate the transaction. That's it. There's no penalty. And here I can have penalty. I don't know if you remember
the HPC case of a few years ago. They found that they were doing several money laundering transactions with one of the customers, or several customers, and the fine was very, very large, millions of dollars, fine. So that's this capability of incorporating a cost matrix is into the C5.0 algorithm and not in the C4.5. So those are the two advantages. It has a rule and a tree version. So it generates rules, it generates a tree. Produces smaller trees than C4.5. Because it combines non-recurring conditions for splits with several categories, and it has a final pruning process which uses a cost complexity approach, and that's intrinsic in the algorithm. It automatically does the pruning using a cost complexity approach. Well, and that cost complexity parameter will be a hyperparameter. So this algorithm has several advantages. One is boosting the number of boosting trials, number of boosting iterations is an hyperparameter. And I can write like that. And also here, the cost complexity, which we call here CP, is another hyperparameter. So I can select those hyperparameters by generalized validation. Validation in several layers. This is a comparison of some of the algorithms you've seen. This is the card algorithm and the C5.0. That's for the iris data. Iris data is a very simple data set to classify because it's the classes are very easy to distinguish. But in the case of the card and the C5.0, give me essentially the same nodes in this particular case. And it gives me also, in both cases, I get a tree of size of, with 3 terminal nodes. Yes. And now we will go to R. Okay. Now please download script. And the script is AM10, árboles de clasificación. You will not need to read any data set because we're going to use the iris data set for this to follow. Sepal width and petal width. My data is iris. Just like that. If I look at the summary, it tells me the classification tree is it tells me that it should fit the function tree in the formula, and so on. And the misclassification gives me here the misclassification error rate. So it misclassified 5 out of 150 observations. That's what it misclassified. Can do a plot. If I do just a plot like this, it will not put any labels. So if I want to take to put the labels, I need to use the text function and do iris3 so I can put the labels. Okay, now I can put the labels, and that's the tree that we saw in the notes. Okay, that's what the labels are. Now I'm going to use the function rpart from the package with the same name, and the function is rpart. The syntax is the same. response as a function of the variables, which is the data set. I do the library R plot, and I use the R plot. Instead of using just the plot, I'm going to use the R plot, and that gives me the display that we saw earlier in the presentation. That has the advantage that it gives me the percentages that observations that I have from the different classes. Okay. And it gives me this the terminal nodes, and that's with the percentages. Okay. And I know, for example, as we saw earlier, here I have 100% of the data. Then once I look at this side, to the left side, I have 33% of the data points are here. So they were Setosa. The other three, there are 66% are here. Okay? That's the display that's here. We can also use a function called library called partykit, which is useful to plot several trees from different algorithms. And I use the plot, and then it gives me this plot. It doesn't look as nice as the other one, but it gives me the bars indicating a relative frequency for each of the different classes. That's with the partykit. Now, C5.0 comes from the package C50, and I'll do the fit with the C5.0. The syntax is the same, okay? And if you see, I'm using the function as partykit to plot it. There's no function to plot the C50 except the plot which is without the labels. Without the labels, right? But here, if I can get a similar plot, I convert the Iris C50 model. This is already the model. I convert it to as an object ASCII variable to be able to make this plot. Okay, and that's the plot I just made here, which gives me the percentages of observations for each class in the terminal nodes. Now let's work with the heart disease data. I'm going to, this is the heart, that's not true, you have to read this file, but you already have this file in your laptops, I think, because we already used it before. It's a heart disease.csv file. Okay? You must have it already in your desktops. Open the connection. Oh, because I didn't copy the file. Jesus. I didn't copy the file. Let me go to. I have the data there, and as you can see, it has a case number, which I don't need to do predictions, age, weight, gender, VO2 max, and the response, which is no heart disease or heart disease. Okay, and I define gender as a factor, and I also define heart disease as a factor. I've removed the first column because I don't need the case number. And I only have left age, weight, gender, VO2 max, and heart disease. Now I'm going to separate, as we said, we need always to do this thing, separate my data. I'm going to use 80% for training and 20% for testing. And I said, that's it. I'm going to do the create data partition the usual way. I select, I do the HD train and HD test, and I do the X train. I'm going to take all the predictors and put them in X train, and I'm going to put all the response and put it in Y tray, and I do the test data, the predictors, in X test, and Y test has the response, right? Now I have, I recall a tray and a response, and I recall it because the algorithms, in most of them use the classes as labels, as variable names. So we cannot have a 0 as a variable name or 1. So I recall them as no heart disease and heart disease. And the same, I do the same thing with the test data. Okay. Specify the levels. And that's the basic tree. Remember the first algorithm used was the tree algorithm, and that is the summary, and this is the plot with the labels. Okay, and that's again the tree that we saw earlier in the notes, where we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terminal nodes. Okay, that's with the tree algorithm. Now, 3HD, if you look at this form, this gives me the tree in terms of, it's almost like an if then else type thing. For example, these can be used to program. You can write a compiler to read this thing and translate that into if then else instructions. So that's one of the advantages of these tree algorithms. Now, I'm going to do a prediction, and to do the prediction, I use the same function we've been using. That's a predict function. I just provide the name of the model. The model is 3HD. And I provide my predictors for the test data and type equals class, because I want to do the prediction for the classes here. And now I can compute the confusion matrix, okay? Confusion matrix, the syntax is the same, it's the predictions, and then the reference. The reference is the response, the actual response on the test data set. And it gives me 70% accuracy, and it gives me a sensitivity of 84%, specificity of 42.8%. Now I'm going to use, with the same data set, we're going to test the CART algorithm, the CRT algorithm. The CRT is run with the rpart function. So I call it rpart HD to the model, and summary, it tells me here the summary of the model, which is the basic information, the algorithm that I ran, how many nodes and stuff like that. And to rpart HD, it gives me something that I can translate into if then else rules for each. Right? Now to plot it, I can use plot just like that with text, and instead of that, I can use the party package to do the plot, which is nicer. Okay? It's a much nicer plot because I have the percentages here of the different classes. Now, to evaluate the performance, I do the prediction with the test set. So I do rpart, I compute now the confusion matrix, and the confusion matrix now gives me an accuracy of 75%, which is a little bit better than the other one, but sensitivity increased, okay? So sensitivity increased to 92%, which in the case of heart disease, it's a good thing to have. Sensitivity is preferable to specificity because of the nature of what I'm trying to predict, which is a heart disease or not. okay? And I can do the other plot with participate, and it's the same thing that we have seen before. Now, this is the way we're going to normally do these things. We're going to be using the train function from Kali to be able to compare different models. I set the control function, strain control. I'm going to use methodical cross-validation. Summary function is a two-class summary because it's a binary classification. And class probability, this is true. I want to obtain the class probability. So that's my control function. Then I took, instead of running the C5.0, the R-part algorithm directly, I run it using the train function from Kali. That's the train function from Kali. It took 0.077 minutes to run. And that's the thing, that these are the results of this is the complexity parameter. If you see here, I did not specify values for the cost complexity parameter. I simply used tune length equal 20 and let the algorithm select 20 values for CP, which is the cost complexity parameter. I'm going to plot it and check here. Since the classes are unbalanced, are not balanced here, we want to use as a criteria the area under the curve. So the area under the curve, we get, it's on the y-axis, and we get very good values here, and then it starts decreasing. So as the complexity parameter increases, I'm starting to overfit. So values between 0 and 0.1 will be reasonable. We've seen what the model has. All models that we compute with the Kali function train will give us exactly the same information. Okay? So they provide the same information. Now, I'm going to plot it as a parity, and the other part, the R part feed of the final model. This is the final model. This is now with the test. No, this is the final model, but it's still with the training data. Okay. Now, if instead of doing the same, I want to use the C5.0, I change the method, and instead of method equal R part, I'm going to say C5.0. Okay. So it's, I think it's C, I forget if it's C50 or C5.1. Let me see if it works like this. And I'm going to call it differently. I'm going to call it C50, C50. Let me see what the word is word. Word. Okay. I left the tune length equal to 20 here. It tells me that there's two hyperparameters here. Trials, there's actually 3 hyperparameters in the C5.0 algorithm. One is we now, the other one is splits, no trials, sorry, trials, which is the number of Boston iterations that I can have. Trials. And the third hyperparameter that I have here is we now, trials, and 3 or rules. Okay? So I gave you 20 values here. I'm going to use a length 10. C50 fit. I'm going to fit it again. And I'm going to say here, there is no R bar, I call it C50, right? C50, C50 fit. See, it's selected. Then for the hyperparameters, it selected rules. Rules generates a rule solution instead of a tree. Tree generates a tree. Then we know, what we now does, it's a variable selection. It selects predictors, okay? We now either we select predictors based on their impact or we don't. So it's true or false. And then trials, it try from 1 through 90, when in fact the trials, the maximum of trials would be something like 11 or something like that. Because we have to, the number of variables is very small. Okay? Doesn't matter, I can do the plot now. Plot C50. Let's look at the plot. Let me clear drawings. See, select no winnowing or winnowing. Winnowing is variable selection, no winnowing is not variable selection, without variable selection. Then rules is the blue line, and tree is the pink line. And then what we have here is the number of boosting iterations. So as you can see, the boosting iterations should be around 11 or something like that, maximum. But the best value for the area under the curve was here with just one trial and no winnowing, okay, without selecting variables and so on. Okay. Now this is the C5.0 algorithm. What I'm going to ask you to do is you're going to do the analysis for, with a blank page here. PowerPoint, and you remember the caravan data? Okay, with the caravan data, I want you to analyze the caravan data. Caravan. You split the data, 80% training and 20% testing. And now you're going to compare logistic regression, K nearest neighbor, K and N, support vector machine with a radial basis kernel, and C5.0. Okay? C5.0. And try C5.0, support vector machine, and then compare the models with the graph that we have done before, comparing the box plots. Okay? So you need to create a list with the different models. And then what we did that with in the script with the support vector machine, that we created a list with the models, and then we created the box plots for the samples. That's what I would want you to do with the caravan data. Okay?
So it's 4 methods you're going to compare: logistic regression, k-nearest neighbors, support vector machines with a radial basis kernel, and C5.0 to compare the carbon data. C5.0 use a tool length of 10. Okay. Or if you remember how to make a grid, it's actually the script for the support vector machine. Do a grid with 3 is win now, true or false. Then it will be the other one will be 3 or rules. Okay, and boosting iterations. Try 5, 20, and how many variables did I have here? I forgot. But let's, or just do a tool length. Don't complicate yourself with that. Just do a tool length of 20. For this one, use tool length 20. Now, make it 10, so it's faster. Because you have more data, erase the whole thing. Just tool length equal 10 for the C5.0. Okay? So it doesn't take us that long. Because we have more data there than with the high disease data. So it's a larger data set. Okay? So it's 20 to 1. So please do that, and then we'll review it next month. Okay? We'll review this comparison next month. Are there any questions?
Yes,
Complaints?
teacher. The next Monday, 15, is holiday, right?
Again?
Yes, I believe it.
Yes, it is.
That is correct.
I have one question. Do we going to have the exam of the 22?